Right. Well, it's our pleasure to have the last talk of today, the talk by Avia Raviv on line defects from magnets and impurities solution lines.
Thank you. So hello, everyone. I'm very happy to be here. And first, I would like to thank the organizers for the kind invitation and the opportunity to speak and present this work. So this talk will be based on this series of papers. The first one, which is based on a work that was done together with Gabriel Cuomo from NYU and Princeton, and with Zohar Margotsky from the Simon Center. The second one, so the first one is about a general theorem regarding RG flows on line defects. The second one, here we studied applications in the context of spin impurities. And it is based on a work that was done together with Gabriel, Zohar, and also Mark Mazei from Oxford University. And these two works that were done together with the same group of people, and also Ofer Aharoni from the Weizmann Institute. And here we studied applications in the context of Wilson lines. So this is the outline of my talk. First, I'm going to give a general introduction into the subject of line defects in conformal field theories. We will discuss the motivation and some monotonicity properties of such system under renormalization group flows. Then, in the second part of the talk, we will discuss applications, and I will discuss three types of applications. The external field defects, line defects in materials, where the focus will be on models of spin impurities, and Wilson lines. And then we conclude. Okay, so let me start with a very broad introduction into the subject of line defects in conformal field theories. Now, we all know that quantum field theory, it is a mathematical framework that is used in order to describe physical systems in nature. Now, it has been successfully applied in many different branches of physics, ranging from high-energy particle physics to low-energy condensed matter physics and cosmology. It is the most accurate physical theory constructed to this day, and it has provided us with dozens of predictions that have been measured experimentally to a great success. So, as we know, quantum field theory is a framework. Namely, it does not consist of a single model. Rather, it consists of many different models that apply in different cases. So one example is the standard model of particle physics that describes the fundamental particles in our universe and the interactions between them. But this is one example. And there are many other models. And in some cases, certain models can be related to each other. And one simple way in which different models can be related is by modifying your partition function by the addition of this term here, for example, or equivalently, you can change the Hamiltonian, where here lambda i's are coupling constants and all i's are general functions or operators of your degrees of freedom, the degrees of freedom in the theory. Now, the most fundamental observation in quantum field theory is that these coupling constants, these lambda i's, they are not really constants. Rather, they vary with respect to the energy scale in which we perform the experiment. So they depend on the resolution in which you probe the physics. So for example, in the standard model of particle physics, the free couplings vary with respect to the energy in which you perform your experiment. For these reasons, that the couplings vary with respect to the energy, the length scale in which you probe the system, people have come up with the following terminology to describe the three possibilities that can happen once you coarse grain your system, once you decrease the resolution. So this is the terminology. We call operators irrelevant if the couplings decrease as you go to long distances in the infrared. We call them relevant operators if they increase as you go to long distances in the infrared. And we call them marginal operators if they do not change as you coarse grain your system. So here in the third case, these are genuine numbers under the renormalization group flow. Now, the actual speed in which the couplings can decrease or increase once you change the resolution, this is model dependent. So for example, in the standard model, they vary as logarithms of the energy scale. Now, a most useful observation of quantum field theory is that typically you have only a finite number of relevant operators. And therefore, if you study what happens to them upon coarse graining of your system, you can make predictions for the theory in the infrared. And therefore, you can relate microscopic descriptions of physical theory to the macroscopic picture. And renormalization group flow is the study of what happens to the system upon coarse graining, and it allows you to relate different theories at different resolutions. Now, typically what happens in quantum field theory, when you go to sufficiently large distances in the deep infrared limit, what you get, a very common situation, is that the theory no longer depends on the resolution, meaning you have scale invariance. And this is what we call fixed points of the RG flow, fixed point of the renormalization group flows. Now, you can find fixed points of the renormalization group flow in many physical examples in nature. So here I put two examples. One is a phase diagram of water, which at the end of the phase transition between liquid water and gas water, it famously has a critical point in which the system possesses scale invariance. Oh, sorry. So this is one example. It appears at very high temperatures and pressure, and it's called the critical point of water. There are many cool videos on YouTube. If you haven't seen, I recommend looking for it. It's cool. The second example is actually a whole bunch of materials in condensed matter. So it consists of many different examples. It's what we call quantum criticality. That is some systems in condensed matter, many different materials. You have the material, and then you have some external tuning parameter. That's a very typical situation. For example, an external magnetic field. And then what happens for many different materials is that at some critical point of the external magnetic field, or the tuning parameter, the system is at a phase transition. Now, it is a second order zero temperature phase transition that is driven by quantum fluctuations. And what happens is that, in fact, there is an entire region in the phase diagram that is characterized by the quantum criticality in which the system possesses scale invariance. Now, two really surprising and beautiful, in my opinion, experimental results are the following.
Can I ask a question before? So,
sure.
So regarding the water, so like what do you scale? What's the invariance?
So throughout this,
you said that there's this critical point that we're
right.
scaling.
So what happens in this scale, in this point, in this isolated point, which is special, is that you can no longer distinguish between the two different phases. There is only one phase, and there is no length, no length scale, no energy scale in the system. Well, you can see it experimentally that you get some weird phase that is not exactly what you call a fluid, not exactly what you call a gas. It's like the two phases coexist in this single isolated point, and you cannot distinguish between them. And you can explain it.
What's the parameter that you
So the characteristic energy scale of the system here, it vanishes. And there is no heat capacity also. There is no latent heat in this point.
You could probably take something, I don't know, fluctuation of pressure, and like it's 2 points in the correlation function, so it would behave like exponent, like as a power law.
Right. And these power laws are exactly what appears here in the first line. So this is, for example, for the systems in condensed matter, there are various quantities that people can measure. For example, the magnetization, the susceptibility, and all these measured quantities that people can measure at the scale invariant regime, they behave like that. where GC is the critical value for the tuning parameter. And these Greek letters, alpha, beta, etc., they are called the critical exponents that describe the system at the phase at the scale invariant point. Now, two very amazing experimental results are the following. One is that if you take many different materials, they seem to share the exact same critical exponents. Namely, there are various universality classes that emerge. And the second interesting experimental result is that all those critical exponents, they seem to satisfy certain relations that make the total number of independent critical exponents less than what you thought in the first place. And this was kind of an open question from a theoretical understanding point of view for many years, until an understanding came from the study of renormalization group flows in quantum field theory. Because what people understood is that these critical exponents are related to correlation functions of relevant operators in the infrared scale invariant quantum field theory. And therefore, by classifying the relevant operators and studying their correlation functions, we can understand the critical exponents that people can measure in the lab. Now, we can also understand the relations between the different coefficients in this analysis. And moreover, it is very often the case in quantum field theory that theories with different microscopic details can flow to the same scale invariant quantum field theory in the infrared. And therefore, it naturally explains the different universality classes that emerge.
May I ask you mentioned that sort of in many different materials, the critical exponents are the same, but sort of would the GC be very different from materials to material, or?
The value can vary. It depends on your system.
Okay.
The value can vary, but then you calculate them for all the quantities that people can measure, and you get that there are a bunch of universality classes. Like most materials fall under the 3D IZ. Many materials belong to the same quantum field theory description.
Okay.
And in fact, it turns out that in these examples that I showed and in many others, the symmetry is in fact bigger. It's not just scale invariance. And generically in quantum field theory, in specific models, it is also very often the case that having scale invariance implies, in some cases, an invariance under the full conformal group, the SOD plus 1,1 in a d-dimensional Euclidean space. And actually, so this is still an open question, understanding exactly what are the conditions for having scale invariance implies having conformal invariance. Understanding and classifying the conditions in which this happens is still an open question that is under active study even these days. And well, quantum field theories that are invariant under the full conformal group, we call them conformal field theories. And now a natural question, which will be the focus of this talk, is what happens once we add defects to a quantum field theory. Now, in general, you have two completely equivalent ways to think of defects, and I will focus on line defects, but to think of defects in a relativistic quantum field theory. One way is you can think of your defects as some extended operators that are inserted into your bulk quantum field theory. And then when you calculate expectation values, you can calculate them in the presence of these extended operators. Okay, this is one way. Perhaps more practical approach is the following. You can think of your bulk theory and your defect theory together as defining some new theory that we call the defect quantum field theory. So here you work with a new Hilbert space. And in this approach, it is convenient to work with a Lagrangian density that consists of the bulk's Lagrangian density plus a Lagrangian density that is localized on a one-dimensional region in space. One-dimensional because I'm focusing on line defects. And this defines a new Lagrangian density that we call the defect quantum field theory Lagrangian density. Now, a simplified asking what happens to quantum field theory when you add defects to them, it's a big question. A simplified scenario, that is yet of a huge physical importance is when the bulk theory is a conformal field theory. So I will be talking about systems that are line defects, namely one-dimensional defects. Can be a straight line or any other shape. One-dimensional defect that is put inside the bulk, that is some d-dimensional CFT. Now, such a setup is relevant for various physical setups. There are many examples. So, for example, in 2D, we have lattice systems with impurities, condo models. In 3D, we have symmetry defects, monodromy defects, and impurities in magnets. And in 4D, we have Wilson or tooth lines in conformal gauge theories. So there are many examples. And to better explain the motivation, let me elaborate on what are we after. So we would like to measure or to compute the response of a system that sits at criticality, namely some quantum critical system at zero temperature, for example, to the insertion of a defect. So for example, you can think I have some system at quantum criticality in condensed matter, and then I act with an external magnetic field, but localized in a point. So this creates a line defect in space-time. Another example, you can imagine I have again some lattice, and then I inject an impurity to the system. And I ask what is the response of the system to such an injection of an impurity. Another related question is if we have a nuclei, what happens, what is the energy that is being radiated by the heavy nucleus in the presence of charged matter fields? And by asking what is the response of the system, what we really mean is if we take measurements away from the defect, which theory do we see? And it turns out that generically at large distances, the expectation values, the correlation functions are very well predicted by the concept of what is called a defect conformal field theory. So let me explain what that is. So in this talk, we will consider systems that are local, reflection positive, Euclidean conformal field theories in some number of space-time dimensions d, can be larger or equal to 2. And then we will add a line defect to it in a way that preserves the reflection positivity and locality. This is an assumption. So now the definition. When people say a defect conformal field theory, or a DCFT in short, then this, by definition, refers to the conformal fixed points. Namely, that for example, for the straight line, namely, it refers to the points in which the defect preserves the conformal group on the line. So for example, for the straight line, if you have a straight line defect in this direction, with xi, the coordinates are orthogonal to the line. So when the system is at the conformal fixed point at a DCFT, then you expect to have SL2R times SOD minus 1 invariance, where this part is the conformal transformations along the line, and this part, the SOD minus 1, is rotations in orthogonal directions. Now, this part is in fact not entirely necessary. This condition can be relaxed, but this is the crucial part, namely the conformal group on the line. And just a comment about line defects at the conformal fixed points is the comment is that they do not support defect stress tensor. And the reason is simple. The reason is that for line defects, the defect stress tensor has only one component, and then the worded entities of conformal invariance, they demand it to be traceless, and hence it does not support a defect stress tensor once it's at the conformal fixed point. The physical interpretation is simple. It's just that you cannot store energy on the line defect once it's at the conformal fixed point. And energy ends up being smeared into your bulk theory. Oh, yes.
Is there a reason that shouldn't expect like a semi-direct product of this?
The what?
Is there a reason I shouldn't expect like a semi-direct product of this rather than a direct product?
Well, that's just for the straight line. For the straight line, it's just the conformal group on the line. You can find examples in which there are no SOD minus 1. It's not crucial, but the SL2R is the definition of the fixed points. Now, it is well known when we talk about ordinary conformal field theories with no defects, just CFTs, then it is well known that they are characterized by the operator spectrum and the algebra, namely OPD coefficients and scaling dimensions. It is also well known that the space of all the possible relevant operators parameterizes the space of possible RG flows that can take place. You can start with some CFT in the UV and turn on some relevant deformation and get some general quantum field theory. And we also have many examples of monotonicity theorems that in general constrain the RG flow and guarantee that in some cases the conformal field theory that arises in the infrared is different than the conformal field theory in the UV. So for example, I wrote a few examples here. The homologic of C theorem, so there is the central charge C in 2 dimensions, and under RG flow we know that the C in the UV must be larger or equal to the C in the IR. So you know that the 2 CFTs must be different. And a very typical goal that physicists are often interested in is to find or to characterize the conformal field theory in the infrared that is given by the deep infrared limit of the quantum field theory. And similarly, when we talk about line defects in conformal field theories, then the defect operators are classified according to the quantum numbers, the SL2R quantum numbers. So for example, for the straight line, the 2-point function of defect operators, scalar operators take this form. We also have bulk to defect OPE that relates bulk operators to defect operators. And in analogy with the previous slide, we can turn on our G flow on the line defect by turning on some relevant perturbation that is localized on the defect. So here, I start with some DCFT in the UV, and then M0 is a mass scale. O hat is a defect operator that is relevant on the line, namely it has scaling dimensions smaller than 1. And then I can turn on our G flow localized on the line. And a typical goal that people are interested in would be, in analogy, to find or to characterize the DCFT in the infrared. So imagine I start with some DCFT in the UV and I turn on an RG flow on the line. And I can ask, what is the DCFT in the infrared that I expect to have? Now, this is not the most general situation. In fact, it does not always happen. I will also show an example in which this does not happen. Namely, you don't always have to end up with a defect conformal field theory in the infrared, but this is a very general situation and it happens in most cases. And then you can ask whether this defect RG flow is reversible. Yes?
I'm just trying to make sure that's what you're saying. You're saying I'm not touching the bulk theory at all.
Yes. That's right. That's right. That's right. In applications, you can think of it, for example, you act with an external field localized in a point, and you don't do anything to the bulk, for example. Yeah, it stays conformal. That's right. That's the general situation. Okay. And then a natural question to ask is whether this defect RG flow associated with line defect is reversible. Namely, can you go back to the same DCFT you started with if you had a non-trivial flow? And the answer to this question is no, it's irreversible. And the reason we know that is because of the G theorem. The G theorem states that there exists a quantity that we call G that satisfies this inequality. The G in the UV, in small distances, is always larger or equal to G in the IR in large distances. Where this G, so actually log G is defined like that. So this is the partition function in the presence of a defect, and this is the partition function without the defect. And both are defined over the exact same regime, the same geometry. Now, in 2 dimensions, in the context of boundaries in conformal field theories, this inequality was first conjectured to hold in a paper from 1991 by Affleck and Ludwig. And then in 2003, Friedel and Konechny established a proof for the 2-dimensional claim. And what we did in the paper with Zohar and Gabriel was basically extending this result and showing that it continues to hold if you have a line defect in an arbitrary number of space-time dimensions, D. Once the bulk is a CFT. So it continues to hold. I will explain the main result because it's a very it's a general result that holds in many cases. I won't show the proof, but feel free to ask me after. I will just mention two comments from here that you can see. The first comment is that the trivial line, namely if you don't have any defect at all, it has G equals 1 and log G vanishes. And the second comment is that reflection positivity implies that G is always positive. Can be smaller than 1 though. Okay, so it turns out that there is actually more than just this inequality. It turns out that you can actually define a quantity that monotonically reduces through a defect RG flow. And to explain what this quantity is, we need to focus on the following geometry. So now I make the line into a circle. So I have a circular line defect with some radius r that sits just in flat space, a d-dimensional flat space. You can also use any of the other conformally equivalent manifolds, like the SD sphere here in the picture, or the cylinder, whatever you like. And you can use any of these geometries in order to define the following quantity that we call the defect entropy. So this quantity is defined like that, this S here. So you take 1 minus r partial r, where r is the radius of the circular line defect, and you act with this on log G, where log G, it's the same definition from the previous slide. It is, and once you have our G flow on the defect, it can be a function of the dimensional product of M0R. So once you have a defect in a CFT, in general, you can calculate the defect's contribution to the partition function, this log G, and then act with 1 minus r partial r and get the defect entropy. Now this quantity, it's useful because it is free of any scheme ambiguities, and it makes it scheme independent. And in particular, at the fixed points, there is no dependence on the radius, and therefore it reduces to log G from the paper by Affleck and Ludwig. This quantity, what we showed is that it satisfies this gradient formula, where here on the left-hand side we have the gradient of the defect entropy with respect to the mass scale, and here on the right-hand side we have this double integral over the 2-point function of the defect stress tensor times 1 minus cosine of the relative angle. Sorry. A few comments about this formula are in order, are in place. One is that TD is the defect stress tensor. In particular, as I said, it vanishes at the endpoints once the theory is at a conformal fixed point. Second comment is that the right-hand side here, it's free of any ambiguities and divergences. You can classify all the ambiguities in here, that ambiguities that appear at coincident points. Namely, you get delta functions and derivatives of delta functions. And then this factor, this 1 minus cosine, it kills all the ambiguities. So it's what makes this formula so useful. Without it, the formula wouldn't be useful. And also, the 2-point function is negatively positive once you have a reflection positivity, and therefore the right-hand side here is always negative. And yes?
So what was M0?
M0 is the mass scale of the flow.
Okay.
The resolution, you can think of it also as the radius of the line.
Yeah, okay.
Yeah.
So it's the same thing?
Yes.
Yes.
Oh, yes. And so the right-hand side here is always negative once you have reflection positivity. And in particular, it implies that the gradient always decreases under a normalization group flow, which as a consequence give you the inequality, which in the 2-dimensional case reduces to Affleck and Ludwig's conjecture. And therefore, you have a general non-perturbative constraint on the RG flow associated with line defects. Okay, so I can just quickly review what was done before and after this result. So I already said that in 2 dimensions, this inequality was conjectured to hold by Affleck and Ludwig in a paper from 1991. And then in 2 dimensions, in their perturbative regime, then a gradient formula equivalent to the above was proposed in the context of string field theory. And then Friedan and Konechny established a proof for the 2-dimensional claims. There was also an alternative proof using methods of quantum information. And also the inequality was conjectured to hold for line defects in an arbitrary number of space-time dimensions in a paper by Kobayashi and collaborators. And what we did was basically extending the two-dimensional results and showing that they are valid when you talk about line defects in some arbitrary number of space-time dimensions. And also recently a proof by methods of quantum information was also given to this inequality. Okay, so unless there are questions, I will move on to discuss applications. There are in general 3 simple ways to construct line defects in conformal field theories. Of course, there can be more than 3 ways, but these are 3 ways that are simple. The first way is what people call external field defects. That is, you take some conformal field theory in the bulk, and then you take one of the bulk's operators that has scaling dimensions smaller than 1, if you have such an operator in your bulk theory, and then you perturb the bulk CFT by adding a perturbation localized on the line. So this is one way. The second model is what people call models of impurities. That is, you take some conformal bulk theory, you take some quantum mechanics, and then you couple the degrees of freedom of the bulk theory with the degrees of freedom of quantum mechanics by adding some relevant couplings between them. And the third way is what people call Wilson lines. That is, Wilson lines, you take some conformal field theory in the bulk with some gauge group, and then you take some quantum mechanics, some finite dimensional quantum mechanics in some representation of the gauge group, and then you couple the two by gauging the symmetry on the line. Okay, I will show examples to all 3 types. The first example is very, very simple. It's just what happens when you have a single scalar field and then you add an external field defect. Namely, you add a perturbation that is linear in the scalar field. Here, lambda is the coupling constant, m0 is the mass scale, and that's the free action. It's just a free boson, so it's scale invariant. It's conformal invariant, and that's the perturbation. And when we consider it when d is between 2 to 4, such that it's a relevant perturbation. This theory is extremely simple. You can just solve it. And if you solve it, what you get, if you specialize to circular line geometry with some radius r, what you get is that the defect entropy, it goes like this, where C of D is a coefficient. That's the value of this coefficient when D is between 2 to 4. And what you can see is that it is always negative, which means that in the deep infrared, when R goes to infinity, large distances, you get that the defect entropy flows to minus infinity. Of course, the results are still in agreement with the gradient formula. The formula does not assume that there is a fixed point in the UV. But here, this is an example in which the flow does not end in a healthy DCFT in the infrared. It does not terminate. The defect entropy blows up. So this is one example. A more interesting example happens when you take not 1, but 3 free scalar fields in the bulk. You can also take them to be interacting if you like. So imagine I have some lattice, and there is some global symmetry. For the case of the 3 scalar fields, it's a global O3. And then you take one of the atoms in the lattice, and you replace it with like a doping atom that carries a different spin under the global symmetry. So we focused on this question in the paper for the case of global O3. And we considered it in 2 different scenarios. One is when the bulk theory is free, and the other is when the bulk theory is interacting. So how is such a model realized in the language of field theory? So this is run realization. This is the bulk action. A runs from 1 to 3. And this is the defect operator, where gamma is a coupling constant, and A runs from 1 to 3. And TA are matrices in the 2s+1 representation of the global symmetry. Now, when you're close to 4 dimensions, when D is 4 minus epsilon, and when S, the spin of the impurity, is small, then this model was measured in was studied in ordinary perturbation theory. just by Feynman diagrammatics and perturbation theory analysis. And what people found, mostly in papers from condensed matter community, was that this model yields one perturbative fixed point. So that's the beta function. The beta function tells us how the couplings arrive with respect to the mass scale. And it has a fixed point at this value at weak coupling. Now, in general, it is clear that as we take the spin of the impurity to be big, perturbation theory, ordinary perturbation theory, will break down at some point. Now, intuitively, this is clear. It's because the factors that sit in front of Feynman diagrams, they are proportional to positive powers of the spin of the impurity, S. So as you take S to be larger, perturbation theory will break down at some point. And if you do the naive counting, just drawing Feynman diagram and asking when does this should happen, when should perturbation theory break down, you get that it should be broken once S is of order epsilon to the -1/2. However, it does not happen, and perturbation theory only breaks down once S is of order epsilon to the -1. This is kind of difficult to see in the language of ordinary Feynman diagrams, but what we get is that there is a different approach to study this model in the large spin limit. Namely, so to use the different approach, so this is just another realization of the same action, of the same model, where here, so Z is a bosonic by spinor, and it is constrained to satisfy this. This keeps your Hilbert space finite dimensional. And the advantage of using this realization is that after you do a rescaling of the fields, one can identify the spin of the impurity as playing the role of H bar to the -1. Namely that when it is big, you can systematically expand in negative powers of S. And what we found was that in this regime, the model can be analyzed in this double scaling limit, in which you take the spin of the impurity to be large, you take gamma squared to 0, such that this is fixed, and then you get a very interesting phase diagram that occurs. So I will skip some results. I will just say that we use this semi-classical large spin analysis to calculate the beta function of the coupling. And what this beta function gives us is the following, is that if you are strictly in 4 dimensions, you have only a single fixed point, trivial one. However, when epsilon S is between 0 to 1/π, when in this regime, you get that there are actually 2 fixed points. One is identical to the one that was already known by standard Feynman diagrammatics, but there is a new fixed point that appears at strong coupling. At strong coupling because this is the value, and is as epsilon S is between 0 to 1/π. So there is a new fixed point that appears once you use this semi-classical expansion. And also the 2 fixed points coincide once epsilon S is exactly 1/π. And there are no fixed points when epsilon S is beyond 1/π. This behavior of having 2 fixed points that annihilate, that get coincide exactly at the bound at 1/π, it was recently observed using Monte Carlo simulations. I will skip this. I will just explain this. This is what we know about the free bulk case. When the bulk is a free theory of scalars. So here, blue areas are areas that we can understand using the now existing techniques. And white areas are areas we do not yet know how to approach, namely small spin and away from 4 dimensions. And what we get is the following. So you have this red line in which there is only a single fixed point, and it separates the regime in the phase diagram that is characterized by 2 fixed points from the regime which is characterized by no fixed points. So here the flow never terminates in a healthy DCFT. That's the spin of the impurity, this line, S, and this is the number of space and dimension. The case of experimental importance is this case, the 3-dimensional case. And what it teaches us is that there are no, in this regime, there are no healthy DCFTs in the deep infrared that we should expect. And this dotted red line is the naive extrapolation of the red line to 3 dimensions. So if you believe the naive extrapolation, what it teaches you is that there are no non-trivial, interesting DCFTs in the infrared for the case of the free bulk theory. This does not happen once the bulk is an interacting theory. When the bulk is an interacting theory, it does end in a healthy DCFT. But I will not explain this part. You can ask me in the end if you're interested, because I want to have time to discuss Wilson lines. Okay, before, are there any questions?
Sorry, so this non-integer dimension, so it makes sense only in the context of Feynman diagrams on flat space sort of with dimensional regularization.
That's right. But this model, the free model, is special because you can mimic it in simulations also away from 4 dimensions, because well, it's the theory is just a free theory, and the bulk is linear in the field, so it's just Gaussian, you can solve it. But if you solve it, you get non-local quantum mechanics, which is useful for simulations, because then the epsilon is like a parameter in power laws of the theory that you get. And then you can, but of course we use the epsilon expansion more to get knowledge of what happens near 3 dimensions. Sometimes it works.
I'm also very confused about another point. So I thought that the ambient theory is supposed to be conformal from the get-go, but the scalar theory is only conformal in 2 dimensions.
No, it's flat. It's flat space, so it's conformal for our purposes. Yeah, and okay, there is the anomaly, but I mean it doesn't interrupt us.
Okay.
Yeah. And okay, and the anomaly in the bulk is not modified by the presence of a defect. So we don't care about the anomaly in the bulk. Okay, so unless there are more questions, I will move on to discuss Wilson lines. Wilson lines in conformal gauge theories. Now, Wilson lines generically describe the insertion of some proparticle that moves around some world line. We have this famous expression for the Wilson line operator, where gamma is the world line and R is a representation. Now, if you work in the Hamiltonian formalism, having a Wilson line simply changes your ground state due to the presence of the proparticle. However, if you're working in Euclidean quantum field theory, having a Wilson line is just amounts to having a line operator. And a natural question that arises when looking at this expression is, what are the infrared limits of theories of Wilson lines in conformal gauge theories? In particular, in this formula, there is no running coupling. There is no coupling constant. So in what sense are the Wilson lines really labeled by their representation? So this is a curious question, and it turns out that the answer is not trivial. And I will only be focusing on 4 dimensions now, but you can make the same analysis that I will explain also in higher dimensions, so in lower dimensions too.
Just to understand it again, so there's no coupling constant because you're in the conformal regime? I think I missed that last part.
So that's the simplest example when the gauge group is just U1, for example, and you can see. So I can. In general, there is a charge, but the charge is quantized.
Yes.
And therefore, it does not run.
But where is it?
So, for example, this is the action for the U1, and this is the Wilson line. Okay, let me try to answer this in the simplest example, which is just scalar QED. Okay. Mm-hmm. So that's the bulk action. This is the bulk action. That's the defect. That's the Wilson line. So for the case of QED, the gauge group is just U1. So the Wilson line, it looks extremely simple because the gauge group is abelian. And Q here is the charge. And if you write the conditions for gauge invariance, you see that it's quantized. So it must take integer values. It cannot get corrections from renormalization group flows. So there is no running coupling. It's just the charge of the line. You can think of it as the charge of the probe particle that you insert. Something that
Okay, so it's completely independent of the electric charge, coupling constant. I mean,
Yeah.
obviously there's this one.
Yeah,
over
it's
here,
not
so-
E.
So that's okay, so
It's
that's
not
an
E.
extra. Okay, so that's a particle which is not related to your like fermions.
That's
that you
right,
have in
it's
this-
not E.
It's
not the-
extra
it's not the
stuff.
electron
Oh,
charge.
okay, then I understand,
different.
okay.
So I will try to explain how to answer this question for the, yes, sorry.
It's the same question Pablo asked before, just that I'm confused about having these scalar elements around. That's why all the
Having the what?
having the matter fields. Okay, the pure gauge theory. I've been told pure gauge. theory
Okay,
is
so-
a problem.
So I can answer. So this theory, you're absolutely right. This theory is not conformal. It is not a CFT. Here, E runs and lambda runs. And okay, there's the definitions. This is charge 1, complex scalar field, and this is the charge Q Wilson line. So E runs and lambda runs. So it's not a CFT. But for our purposes, we can treat it as if it is a CFT. And to mathematically justify it, you can say that you work in the following double scaling limit, in which you take E squared to 0, you take lambda to 0, you take the charge to infinity, such that E squared Q is fixed. In this limit, when working in this limit, you can neglect any running in the bulk. And then you can treat, when working in this limit, you can treat the bulk as if it is conformal. Of course, in real life, you will still have order E squared corrections, etc. But in this formalism, when you work in this limit, you can neglect them.
So then probably also is going to ruin the second question I was about to ask, which is, does it matter that Wilson lines get to end up on, like, I've been told Wilson lines can end up on charged matter. That's not going to happen in this qubit.
That Wilson lines can end up to what?
Well, I just don't really understand Wilson lines very well, and I was going to ask if it matters, if it sort of affects the analysis that there is a matter field at all.
Well, definitely the question that I presented, it matters if you have charged matter fields or not. Yes.
But you don't, I think I understood your question, but I might be wrong. So you can imagine something like a Dirac string. So you have an electron and then you have this string of photons kind of extending to infinity, right? So I guess depending on the community, we would also call it a Wilson line, but it's a different animal from what you're showing here, I guess, because so my thing would have like your phi of x and then this integral kind of a of x minus y dy.
So it's for my prescription, all you need is a gauge group in the bulk, and then you add some line operators that is like gauging the symmetry on the line.
Pure
That's what
gauge kind of line operator. So it's not
you
attached
fix
to
the
any
gauge
kind-
on the line.
I think that was the question. So in QFT, otherwise there exist things that people for some reason also would call Wilson lines, which are
I
not.
think that's the
attached.
definition. That's the definition. And
I think I understand.
it's just a line defect. It's just a line defect, just a probe particle. Just some defect that you insert. You can think of it as heavy nuclei.
Yeah, I think it's just a language.
Okay. Okay. So this is what I call Wilson line. Charge Q Wilson line, and as I said, it's not really conformal, and you can work in this limit in which you can treat it as if it is conformal. And okay, if you solve the classical equations of motion, what you get is a not surprising saddle point with a zero value for the scalar, and this solution for the gauge field, which is not surprising. It's just a Coulomb gauge field, like we were taught in classical mechanics 2 of undergrads. So that's a very naive solution. It makes sense. And one would therefore naively think that the infrared theory simply consists of a Coulomb gauge field that is created by the probe particle, and that's the end of the story. But it turns out that that's not the end of the story. And there is more to this picture once E squared Q becomes large enough. So let me explain what I mean by that. So to explain that, we need to look at the following different, well, it's convenient to look at the following different defect operator, phi hat, dagger, phi hat. Naively, the scalar field has dimensions 1 in the bulk. So this should be phi hat, dagger, phi dagger, phi should be highly irrelevant. It has naive dimensions of 2. However, you can calculate the scaling dimensions exactly in this limit. So to do that, that's just technicality. We move to ADS 2 times S2, calculate the scaling dimensions. It's convenient for technical reasons. And if you do that, you get that the scaling dimensions for the scalar field, they satisfy this quadratic equation. Delta is the scaling dimension, and they satisfy this quadratic equation. Now, this quadratic equation, what it teaches us is the following, is that if E squared cubed over 2 pi is smaller than 1, you get that there are actually 2 solutions for the quadratic equation. These 2 solutions, so you see here there is a plus, here there is a minus, and then there is the square root. So these 2 solutions correspond to 2 different conformal boundary conditions for the scalar field. So we call this boundary condition the standard quantization boundary condition, and this solution we call it the alternate quantization boundary condition for the scalar. The names will be more clear soon. Well, in natural units, having E squared Q over 2 pi equals 1, because this is the bound. When it's smaller or bigger than 1, you get different phases. So in natural units, it corresponds to having a charge of 68. So if the charge is below 68, you get that there are 2 solutions to the conformal boundary conditions. However, if the charge is bigger, if E squared Q over 2 pi exceeds 1, bigger than 1, you get that there are no real solutions to this quadratic equation. You also see that the square root becomes imaginary. And this is what we call the supercritical regime for reasons that will soon become clear. So let's look more explicitly. So this is the scaling dimensions of the should be hat, phi hat, dagger, phi hat operator, the upper line here in the standard quantization boundary conditions. And you can see the following things. One is that when Q is strictly 0, you go back to 2. That's the old scaling dimensions from the bulk. So this is 1, consistency check. The other, you can see that if you expand this in small e squared Q, you can get results that diagrammatically completely agree with Feynman diagrams. Also, you can see that as the e squared cube over 2 pi becomes closer to 1, what you get is that this whatever is inside the square root becomes closer to 0, and then the defect operator, the scalar bilinear on the line, becomes closer and closer to being marginal on the line. And this means if we have an operator that becomes closer to marginality, we have to add it to the action and see what happens. It means that we must consider a more general defect, a more general Wilson line. And also, from looking at this expression, there is an interesting question of what happens when you're above the criticality, when e squared q over 2 pi is bigger than 1, because then the scaling dimensions become imaginary, and we have to understand what happens there. It's an interesting question. Okay, so I said that we must consider a more general Wilson line. So this is the more general Wilson line. So Q is the charge, G is the coefficient of the phi hat, dagger phi hat operator. So this operator becomes marginal on the line, so we added it to the action. Now, of course, well, Q is the charge, it doesn't get to be normalized, but G can be normalized, and in fact, it does receive corrections. And you can calculate that that's the beta function that we get. And this is exact. This is one of exacts, wall orders. And this beta function, what it teaches us is that if you are below the instability, you actually get 2 fixed points. So that's the plot of the beta function for the different values of e squared q over 2 pi. So here, this is the plot that we get once you are below criticality. And you see that there are actually two fixed points. One that corresponds to what we call alternate quantization boundary conditions for the scalar. And another one that corresponds to the old Coulomb solution, the standard quantization boundary condition. Now, in general, if you start from here, this is an unstable fixed point. If you start from here, you will flow all the way to the old Coulomb solution, to the stable solution. However, if you start from here, you'll have a runaway. The coupling flows to minus infinity. Also, the two fixed points coincide when you're exactly at the bound, and there are no fixed points once you're above the bound. And again, the coupling runs to minus infinity. So now an important comment. What I just said, so just like we looked at the phi hat dagger phi hat operator and seen that it becomes marginal at some point, we can look at other operators as well, other defect operators as well, like a quartic, phi hat dagger phi hat squared, and this can get marginal too at some point. So what we can say for sure is that when you are between charges 60 to 68, then the scalar bilinear is the only operator that becomes marginal on the line. However, if you are below charge 60 or charges 59 and below, other operators like the quartic become marginal as well. And you must add them to your action and analyze again your G flow and see what happens. Between 60 to 68, there are two fixed points, and below that, we are not sure. And as I said, it's interesting to ask what happens above criticality. Clearly, from the beta function, the G flows to minus infinity. So intuitively, we expect some new non-perturbative dynamics to appear. And what happens in practice is that when E squared Q over 2 pi is bigger than 1, the electric field is so strong that it starts creating pairs of phi hat dagger phi hat on the line. And there is this condensate that is created on the line, which subsequently triggers a condensate in the back as well. And there is this scalar cloud, that's the condensate, that is being formed. And what we found is that the scalar cloud completely screens the Wilson line, in the sense that in the supercritical regime, the Wilson line in the deep infrared become completely trivial. What we mean by trivial is that if you look at one-point functions in the buck, away from the scalar cloud, they all just vanish, as opposed to ordinary Coulomb solution. So this is what we get when you're in the supercritical regime. This is the numerical solution. So here, E squared Q over 2 pi is 1.02. So you're just a little bit above criticality, right? Namely for charge 70. And here, so that's the distance. And in orange, it's the electric field when normalized by R squared. So you see, it started its life as a Coulomb, just a constant E times R squared. And then it starts decaying until it is completely screened. On the other hand, for the scalar, it starts its life with 0 VEV. And then there is this condensate that is being formed. And eventually, it is also screened to 0, although slower. And in this, at the end, the infrared theory that you get is completely trivial. Also, similar behavior happens if you start below criticality, but from the left side of the alternate quantization boundary conditions, from the regime in the phase diagram in which the coupling flows to minus infinity. So we found that when the charge is between 60 to 68, there are actually two different DCFTs, and there is like a double trace flow that takes you from the alternate quantization to the standard quantization boundary condition. And also we found that Wilson lines above criticality, above the critical charge, they are unstable and they do not define a unitary DCFT. And in the case of scalar matter fields, we found that the Wilson lines are completely screened by the charge scalar matter. Now, it turns out that the analysis is quite general. It's very general. You can apply it to any case in which you have charged metal fields and some gauge group. So for example, the natural question is, what about ordinary QED like we have in nature? So you can do the analysis there, and what we find is that it's kind of similar to scalar QED that I discussed. There are a few differences. One is that the criticality appears at E squared Q over 4 pi instead of 2 pi equals 1. And this gives us a critical charge of 137, which might ring a bell because it's 1 over, okay? And also the fact that there is something curious about the Dirac field in the presence of Coulomb gauge field for charges 137 and above. It's not a new fact. It was known, in fact, from a paper by 1945 by Kumarenchuk and Smoledinsky, where they seen that the solutions to the Dirac equation in the presence of this Coulomb field, they get their scaling dimensions become imaginary at some point. So it makes contact with this. Also, another important difference is that in the case of fermionic matter fields of ordinary QED, you get that there is just a partial screening. Like if you start a little bit above criticality, you will be screened up to a charge 137, and then it stops. Now, one can calculate it using the energy spectrum. It's a lot of technical work, but this was done. And you can see that the system prefers to stop creating pairs of fermions by linears once you get to the critical charge. Intuitively, it's because of the Dirac statistics, Fermi-Dirac statistics, that you cannot put all the fermions in the same place. You need to put a fermion, and then the next one is a little bit above in the energy spectrum, etc. Well, in the contrast to the bosons, that you can place them all in the same ground state, and that's it. So it costs more energy to create a fermionic condensate. Also, you can repeat the analysis for non-abelian gauge theories and have applications, and the similar things happen. Like you can also work strictly in n equals 4 super Young Mills, which is conformal. You don't need a double scaling limit there, and then then you can get similar conclusions. Now, of course, in nature, we don't have a charge 137 at all. It stops somewhere at 118. However, you can see this phenomena that I discussed, the screening and the cloud of the matter, if you discuss systems of graphene. Because what happens in graphene is that the fine structure constant is much bigger than 1 over 137. It's like 2. And then you can see this effect in a real life laboratory. And this picture, it's from work of a group in MIT, and they observed that this is for graphene, and this is, you can see the fermionic cloud that is being formed, and then the screening. So this phenomena that I discussed, it makes context with this phenomena in graphene, but from the theoretical point of view and the language of defect conformal field theories. Okay, that's all I wanted to say. I will quickly conclude. Line defects in conformal field theories, they provide interesting setups that are of relevance to various physical systems. They exhibit monotonicity properties with the existence of a monotonically decreasing entropy function for the defect. I discussed various types of applications. Also, it's interesting to note that there are certain similarities between models in condensed matter and Wilson lines in conformal gauge series in high energy physics. In particular, for example, the annihilation of the two fixed points exactly at bound. And also you can use similar methods to study both systems. So that's it. There are many questions for future research, but I will stop here because I'm over time as it is.
Can you go back to this slide with this modified Wilson line? Just trying to understand the physics. Okay, good. So that actually looks very similar to what I would call a Wilson line, with just the modification that this phi dagger phi would not be in the exponential, but you have something like phi dagger, then p times this exponential, and then phi. Would you have, so what's wrong with that object? Phi dagger, then the path order exponential.
Just a billion, we can just forget about the path ordering, and you could think of it as just that's the action. Maybe it's more simple like that. Yeah, that's the action. You can add here plus g phi dagger phi integrated on the line. It's the same.
No, but that's okay. Maybe the question is stupid. If the question is stupid, please do tell me.
No,
I can
I
take
just
the
don't
position.
understand.
But so in QED we have observables where you have like electron, and then you have a cloud of photons, and then you have another, say, positron, right? Electron, positron, and these photons in between.
Like scattering processes.
No, well,
Well, this is an infinite Wilson line, right?
Yeah,
It doesn't start and end anywhere.
yeah.
yeah. So what
With
I'm
that,
asking,
from
okay,
minus
so what I'm
infinity to
asking
infinity.
is there a problem? So can I, in this formalism, include a Wilson line which does start and finish somewhere, or is there a fundamental problem with that?
Well, we want to preserve gauge invariance.
Yeah, but these are gauge invariant observables.
So here the Wilson line, like you can transform AT to AT plus DT lambda. And
No, my observable
You
is
can-
also gauge invariant.
so you can,
But it doesn't matter. You just don't, so you don't. That's fine.
yeah,
I thought that.
it's an infinite.
You want to be able to zoom out. It's supposed to be like a conformal.
Because if you
Yes.
take these things, okay, so it's like I'm looking it from very close up, and then
Right.
it looks infinite.
Something like that.
I buy it.
Yes.
So you mentioned those non-abelian Wilson lines. So there, would you have like this flow which would like above some
I can show you. I
maybe
have a slide in the backup slide. I can show you.
station go completely screen, or would you have
So
some representations? flowing
representation.
Other ones?
Representation, you're absolutely right, it's representation. So that's the non-abelian case. Can you see?
Yeah.
So here, for example, we studied n equals 4 super young males in the bulk, and then the gauge group would be SU2. We took it to be SU2. And so A runs from 1 to 3. And then we take the representation to be large and G young male squared to be small. And okay, the body conformal, but we take this limit to analyze the behavior. And what we get is that Wilson line become unstable once the representation is such that G young male squared times S is of order 1. So for the case of super young males with great group SU2, you get that the first particles to develop an instability is the scalar fields. And this happens once this is 2 pi. And what this means is that if you are the given G young males, for some large representations, the Wilson lines stop to exist. It also has applications for, if you are familiar with those flows that the flow that was proposed by Kolchinsky and Sully from the ordinary Wilson line to the 1/2 BPS supersymmetric Wilson line. Because the starting point of these flows, this shows that it becomes unstable for some large representations. And however, the supersymmetric lines are completely stable, as you would expect from the fact that they should have 0 energy, but also you can calculate it. And that's like the scaling dimensions for scalar bilinears in once you have also supersymmetry. And you can see that when the supersymmetric point is just there are no instabilities.
But do you know how, like for higher rank, for instance, for rank 2, without supersymmetry, how would it run depending on the parameters? Because one can imagine that instead of complete screening, it would run to like screen like one of the components and not screen the other one. Or this would
So here the screening is for this case that we analyzed, the screening is very similar to the scalar QED mechanism, in the sense that the scalar fields get screened first and you get a trivial line.
Okay, thank you.
Right, let's thank the speaker again. That's it for today.
I'll send you a different slide. Same slide, but without the data.
Question?